Thank you for the introduction. Today, I'm going to give a talk about where and how our brain represents words. So, as a human, we can describe infinitely diverse experience by limited number of words. This further promotes the communication between people. Researchers in various fields have been interested in how our brain makes this happen. And early neuroimaging studies used contrast between words and non-words to localize where the brain represents words. However, such methods cannot be used to answer how a specific word is being processed. And in the last decade, people start to use computational models to predict brain activation when processing word meanings. Some of them use the human-defined attributes. This has advantage to interpreting the neural system. But both of these works studied like isolated words and short sentences. However, in real life, word meanings are not isolated from their backgrounds. They bear complex relationships from one and another in the diverse context. So recently, the work from Hughes and his colleagues used naturalistic stories to map word representation with fMRI response. The semantic content of words was mapped into real vectors that represent the word co-occurrence in 985 common English words. Their results shows the most areas in the semantic system represents a specific group of concepts. However, the semantic model they used was based on hand-selected keywords. This may be biased by human evaluation, and it may not evenly cover the semantic space. Such technique of mapping words into vectors in continuous space is called word embedding. So instead of using keyword attributes, word-to-vec model is purely data-driven and was trained unsupervisedly. It learns the word representations that best predict the nearby words in diverse contexts. In the word-to-vec space, words share similar context and tend to cluster together. And the semantic relationship between words can be reproduced by vector arithmetic. For example, like king minus queen is similar to man minus woman. So in this talk, I will introduce our findings by mapping this word-to-vec representation to brain activities when subjects are listening to continuous naturalistic stories. So from the same semantic representation of words, we built one computational model to predict high gamma ECOG on epilepsy patients, and another computational model to predict fMRI responses on healthy subjects. We further compared the results from these two modalities. This helps us to answer where and how the brain represents words in neuronal timescale, and also allows a whole brain analysis to discover the cortical networks during word comprehension. So the ECOG was recorded on the left hemisphere in one epilepsy patient. The patient listened to over 2 hours of diverse stories. We filtered the ECOG to extract high gamma power from 70 Hz to 150 Hz, and the individual words in the stories was converted to vectors by a pre-trained word-to-vec model. So in this way, the stimuli can be viewed as a trajectory in this 300-dimensional space, whereas temporal variation carries the semantic meaning in word level. To model the neural encoding of words, we defined a multivariant multiple linear regression model to use the word-to-vec representation to predict high gamma power. And the model performance was evaluated as the cross-correlation between predicted and measured high gamma power. So among 78 channels, 18 of them can be significantly predictable, and the highest prediction accuracy was found along the superior temporal gyrus. So we extract the predicted high gamma power in one testing data to demonstrate how the model performance in this specific channel in superior temporal gyrus. And by zooming in, we can further match each words in the time series to see how the continuous word information trigger the fluctuation in high gamma power. So now we have got a bunch of locations that carries word meanings. One interesting question would be whether these locations carries or encodes the word meanings at the same time. So with the high temporal resolution of ECOG, we can answer this by using a latency analysis. How we do this is, for each channel, we manually lag the high gamma power behind the speech stimuli in a variable delay. And the estimated latency was defined as the lag that with the highest prediction accuracy. So the results suggest the shortest latency was found in the center of superior temporal gyrus and increased gradually in the surrounding areas. And the lag in the premotor cortex is around like 100 milliseconds to 200 milliseconds, while in the subtemporal areas it's longer than 400 milliseconds. So these results tell us that in different cortical locations, it encodes words at different time, and higher order cognitive areas tend to have longer delay. And this may suggest a hierarchical processing of word meanings. So to better understand how words are encoded on a whole brain scale, we did several fMRI experiments on healthy subjects using the same sets of stimuli. And we redo the linear regression to get a new predictive model with the same sets of word-to-vec regressors. So the model best fitted at widely distributed cortical areas, including prefrontal cortex, inferior frontal cortex, inferior parietal cortex, lateral temporal cortex, and posterior cingulate cortex. And the left hemisphere fits slightly better than the right hemisphere. This pattern matches very well with the results of semantic system from Jeffrey and his colleagues, which combined over 120 neuroimaging studies. We also test our predictive model on new sets of stories, and the following areas shows the best prediction accuracy on both hemispheres. By demonstrating the fMRI responses, we can notice that although all these areas can be predicted quite well, their temporal variations are actually distinct at different cortical regions. And now we have two predictive models, one for ECOG and one for fMRI. One would ask whether what information is encoded similar by these two modalities. So to answer this, we cross-correlated the encoders for ECOG and the encoders for fMRI to see whether it is consistent. For example, in this specific channel in superior temporal gyrus, it matches with a bunch of voxels in fMRI in the related areas. Since the word-to-vec regressors are the same for these two predictive models, this suggests that the word representation encoded by these two modalities are somehow similar. So now we have seen widely distributed cortical regions contains word information. So one would ask how the specific word information is encoded by these different areas. With the predictive model, we can do several computational experiments on it. For example, one interesting question is whether a specific concept is encoded by a particular region or distributed cortical networks. To achieve this, we can first manually select a group of words with the similar concepts and predict its fMRI responses. And by averaging all these fMRI patterns, we can generate a semantic map for this specific concept. For example, the human-related nouns are mostly activated the superior temporal gyrus, but also activated partial of the inferior parietal cortex, inferior frontal cortex. While for the prepositions, it's spread much more widely in inferior parietal cortex and prefrontal cortex and lateral temporal cortex. We can also generate the semantic maps for verbs, foods, and time and numbers. And another interesting question would be, how are these different cortical regions communicate with each other during word comprehension? To answer this question, we can do a k-means cluster on the encoders, and the result shows that we can get 9 different clusters in the best predicted areas. Most of these clusters are bilateral and contains distinct cortical regions. Notice that the fMRI responses being predicted only contains the information regarding word meanings. So this result suggests that there are probably some subnetworks in the semantic system that plays the different roles during word comprehension. So to sum up, our findings suggested that the superior temporal gyrus represents words during natural speech. And words are encoded in different legs for distinct cortical regions, and higher order cognitive areas tend to have longer delay. From the fMRI results, we found widely distributed cortical regions that encode word meanings, and group of words are represented by distinct cortical networks. So brain activities regarding word comprehension can be clustered into several subnetworks in this large semantic system. So inspired by this work, there are many interesting questions remain to be solved. For example, we can use the same method to build a predictive model for bilingual subjects when they are listening to stories in different languages. And by mapping a deeper language model to the brain, we might be able to explore the hierarchical processing in language system. And from the model perspective, it would be interesting to see if we can combine the results from ECOG and fMRI to better explain our questions. And thank you for my co-authors and collaborators. And thank you for your attention.
Do you have any questions for Yizhen? Very, very impressive work. Just curious, because it's very interesting that you're trying to map out different words activating different regions. Have you also looked at dimensions of imageability or abstractness, concreteness of the word frequency?
Yeah, that's an interesting question. So actually, we in this exploratory work, we are only focused on the word meanings. Haven't look into the frequency, but it would be interesting to see in this diverse context, in what frequency or in much higher levels, like phrases or sentences, how they encoded. Thank you.
Thank you.